So I will wait for about 1 minute before start. Okay, so let's get started. Can everybody hear me? Would you say yes if you can hear me? Okay, so thank you very much. Let me share the screen. Okay, so let me activate the chat here. Okay, so where we are. So we have been discussing, here's a quick reminder. Of what we have been discussing so far. So we have been discussing about the syntax and semantics of predicate logic. And we talked about its syntax, which was an abstract syntax. And then also we defined its denotational semantics. And we also looked at some of the inference rules, which is about the rules that allows to show, derive valid inference rules. Okay. So, and then as I said, one of the reasons we study predicate logic is because it's a simpler, in a sense, artificial language, which have many features that you will see in programming languages. And one of the features that appears in predicate logic that also appears in many programming languages is called binding. Very simple way to think about binding is it's a way to declare a local name or local variables that's roughly correspond to local variable declaration in most programming languages, but in more general setting, binding construct can allow us to bind not just local variable, but something more sophisticated. And in any of these binding constructs, there are some principles, so language design principle one has to respect. And these are there are ways to analyze the behavior of binding in terms of substitution. So that was what we were in the middle of discussing when I finished lecture last week. So in particular, what we discussed about was a substitution. In the presence of binding. Okay, but before going further, let me just mention the principle that I told you about binding. The one principle is that renaming, if you have a local variables, I mean, in the predicate logic, if we have a quantifier like for xp, this x, I mean, the particular name or variable that we introduce doesn't really matter. All we say here is that we want to introduce a new variable. It happens to have a name x, but if it has a name y, it shouldn't really matter. So we introduce variable x, then we make it available inside the p, and this meaning is x is universally quantified. So in order for this to be true, for all bind value of x, p has to be true. But then intuitively we think that its meaning should be same as meaning where we rename x to y, okay? Where y doesn't appear as a free variable p, minus x. So we pick some fresh variable y and we rename variable x to y. So then the meaning should be preserved. And this is the kind of one of the principles that most of the binding operators that we'll encounter should satisfy. And it turns out in old days, when people introduced a mechanism for binding local variables, they use so-called dynamic binding, and dynamic binding doesn't satisfy this property. So renaming doesn't preserve the meaning. So in some sense that indicates dynamic binding is not exactly what we have in mind. So it's in a sense wrong. Or another way to understand dynamic binding is that it's something different from what we normally expect when you introduce names like by the universal quantification and so on. Okay, so let's go to the main part that we were in the middle of discussing. The main part was substitution operator. So substitution operator it's a mapping from variable to integer expressions. And then when we define the substitution intuitively, what we define an operator, okay, we define an operator for the p delta. What it does is that it substitutes all free variables in p using delta. Okay. But one important aspect here is that we only care about free variables in p. So we are not this substitution operator are not supposed to change any bound variable in p. It will only have to replace the free variable. So for instance, if you have a substitution, so this idea of only replacing the free variable actually makes this definition of the substitution a bit more subtle. And there are two cases we have to consider. Maybe you can say two pitfalls. So two places where we can if we define substitution in the wrong way, there are two possible problems that you will encounter. For instance, if we have for x is greater than y, then if we apply substitution x arrow y, which means that replace x by y, all the other free variable, it doesn't do anything. So that's what this substitution is telling us. If you apply this substitution, then intuitively the outcome has to be for x greater than y. Although x appears as a bound variable, the same name x appears in the formula as well as in substitution, we shouldn't do the replacement because substitution is only about free variables. Okay, so this is okay. What's not okay is that for x, y greater than y, that's not okay. Okay, so that's the one possible problem. So that means sometimes if we define substitution the wrong way, we end up with replacing bound variable, not just free variable. So the second problem is a bit more subtle. So this one has even name, which is called variable capturing. So let's look at the same example. But this time, let's say we're going to want to replace y by x plus 1. So then you might think that, okay, y is a free variable here. So if you replace y by x plus 1, you might think this outcome has to be for x greater than x plus 1. Actually, this is wrong. Why is that? That's because when you write a substitution, like y becomes x plus 1, the variable x that appears here refers to free variable. not a bound variable. Okay? We are saying replace free variable y by an expression x plus 1 where x is a free variable. So that's what we mean by this substitution. But after this substitution, you can see that the outcome, this variable x, now get bound to the universal quantification. And this is the incorrect application. So what we really have to do in the correct, okay, the correct definition of substitution is that we should rename this bound variable by something else, x new. So that, I mean, this phenomenon where the supposedly free variable get caught by the bound variable, this is called variable capturing. And what we have to do is that we have to define substitution in such a way that variable capturing doesn't happen. And the idea is because the quantified variable, its name is not really important, we rename it before applying the substitution. And then after that, we name x to something else like x new. And then only after that, we apply the substitution. Y becomes x plus 1. So if we do so, the one below becomes x new greater than x plus 1. So variable capturing in this case doesn't really happen. So this is okay. And the one above is not okay. So that's the two typical problems that we want to avoid when we define substitution. So then here's an implementations that avoid these two typical problems. So how we define substitution? And so we define substitution by structural inductions. So, or maybe you can say it's an application of substitution. It's defined by, well, not in a syntax-directed way. And that means we will do case analysis on assertion P. And then for each of the case, we will define how substitution should be. This application of substitution should behave. And the simple cases are really easy. If P is true, then if you apply the substitution, that is equal to true. If it's false, if you apply the substitution, that is equal to false. And other cases are also quite easy. If you have an equality or less than to apply the substitution, then this time we recurse, but we do the application of substitution to expressions that we already studied before. So this case is a E1 where we apply the substitution, then we maintain an operator, which is either equality or less than, and then we apply substitution to E2. And other cases are pretty similar. So if you have a conjunctions, apply the substitution, that is, we recursively apply substitution to P1, and then recursively apply substitution P2, and then combine them together. And negation is also similar, apply the substitution, then we apply substitution to P, and then put the negation outside. So what does this mean? This means that you just go all the way, essentially move substitution all the way to the base case, which is going to be an expression, and also move all the way to the base case of integer expression, which will be a variable. Only then we apply the substitution. So if I ask you, to define substitution, application of substitution in an exam, I think most of you will get this much right because it's not very difficult. But a bit tricky part is to dealing with the universal quantification, also existential quantification, but I will only explain how to deal with the universal quantification. So if you have a universal quantification like this, then essentially to avoid these two problems, we have to make sure we are not applying the substitution to bound variable x. Okay, that's one thing we have to do. And then second thing is that we have to make sure the variable capturing doesn't really happen. So how to do this? Then the first things, so to avoid the first problem, so here's a wrong definition, but that allows us to avoid the first problem. How to avoid the first problem? The way to avoid the first problem is when you apply substitutions on the body of the universal quantification, we change the substitution, okay? So that x gets mapped to itself, which means that for bound variable x, you don't apply any substitution at all. So now if you do this, then for the first example here, the problem won't happen because now when we go inside the body of universal quantifications, our substitution will essentially become an identity for all the variables. So that first problem doesn't happen, okay? So this is a way, it's a device that allows us to avoid the first problem. But it doesn't let us avoid the second problem, okay? Even if we just apply this definition to, the example here, then we will see that the same problem happens. So what should we do? So the idea is that the second fix is instead of just using x, we potentially rename bound variable to something called x new. So we just erase this. Say x new. And then the other part, now we said the bound variable x inside the p will be renamed to x new. So then the question becomes what kind of variable x new we should use. So here's the conditions for x new. So x new should be the one which will not do variable capturing, okay? It will not cause the second problem that I talked about. And how to ensure x new doesn't really cause the second problem. And the way to ensure is that it's not going to appear in any so it will not appear in any free variable of applying substitution to y, where y is something that can be, so it's some variable appearing in P except x. So what does this whole formula mean? This means that for every variable v, y, that appears in P except this specific bound variable x, okay? For every free variable y, these kind of free variable y will be replaced by the substitution, okay? So these are the variables that will be replaced by the substitution, and the substitution will replace them by this guy, okay? So we look at what's gonna appear when you apply the substitution on variable y, and also collect all the free variable there. So that's what this one is telling us. And variable capturing means that some of these free variable all of a sudden becomes bound. So we have to make sure this kind of thing won't happen. So we have to say, actually we have to say this x new should not belong to the this union of free variable of delta of y. Okay. Any variable y appearing in P, so if I just draw a picture, P may contains y1, may contain x, may contain y2 as a free variable and so on. Then if you apply the substitution, this y1 will be replaced by delta of y1. y2 will be replaced by delta of y2. So when we do the renaming x to x new, we have to make sure x new doesn't really appear in here. It doesn't appear there. Also, x new doesn't appear here. So that variable capturing issue doesn't really happen. So that's what this condition is telling us. Now, if you look at this condition, the condition is a bit non-deterministic. It doesn't really say which specific x new we should use. So in the textbook, John make a convention which said he assumed, okay, so So actually, most of the theory that we are talking about, which x, what theorems that we talk about, which variable x satisfying this condition should be picked, doesn't really matter. All the theorems will continue to hold. But if you want an algorithm, then algorithm, according to John, looks like this. So if x itself satisfies these conditions, same as x, if x satisfies the condition. What does this mean? This means that if x doesn't do any variable capturing already, then just use x. Otherwise, pick the first variable satisfying the condition. So it assumes that the variables are, there is a enumeration of all the variables, starting from the first, second variable, and so on. And you pick the one, the first one that satisfies this condition. So that's what's described. And this is the kind of issue if you want to implement the substitution as an algorithm. Okay, so what can we say about this? The first thing we can say about this substitution is the following. So there are three properties that we're gonna talk about. And they are also something that we studied when we some simplified version of this we studied when we looked at the language for integer expressions. So I think right. So the first property is correspondence. So what the correspondence say? Correspondence says actually this correspondence is not quite about the substitution, but this correspondence is one important property. And this correspondence lemma says the following. If you have assertions, so formula and predicate logic, and we have two states, sigma and sigma prime. So what are the states? States are mappings from variable to integers. And then we will give for sigma and sigma prime say the same thing for all free variables in P. So then set this semantics of P on the sigma should be the same as the semantics of P on the sigma prime. So what is semantics? So semantics of P should be a mapping from state to the sigma. Yeah, so this is called sigma to the Boolean. So the first statement say that for all the free variable in P, if sigma and sigma prime say the same thing, then P on the sigma prime should have the same value. And the proof of this, so the same kind of things we also said in integer expressions. Given an integer expressions, if you have two states which give the same value for all free variables appearing in integer expressions, then integer expression will mean the same integer values on those two different states. So this is a similar kind of result, which intuitively say the value of assertion only depending on the value of free variables. Okay. Now how the proof is by structural induction. What does this mean? This means that we're gonna do case analysis of all the possibilities of X, P, and then we use induction to complete the proof. So it's a case analysis on P, and proof using induction hypothesis. So instead of for me to do it, I want you to, complete the proof. And I don't expect you to do the proof for all the cases, but only deal with the case where P is equal to true. So I use this triple equal to emphasize P is syntactically the same as true. And the second case is P same as P1 and P2. And the third case is P is universally quantified case. Okay, so complete this inductive proof. I will give you 3 minutes to complete this inductive proof by completing the proof for these 3 cases. Okay, so let me show how to do this. The first case, what we have to show is that P is sigma, same as P under sigma prime. So this is what we have to prove, but the left-hand side is equal to true. Because this P is equal to true, the right-hand side is equal to true, so that's why this is the case. And then for the seconds, what we have to argue is that the free variables of Pi, P1 or P2 is all included on free variable of P. So the sigma and sigma prime satisfy the assumptions of the lemma for P1 and P2. So this means we can apply induction hypothesis. So by applying induction hypothesis, we can say P1 sigma is equal to P1 sigma prime. Also P2 sigma is equal to P2 sigma prime. And if you bring these results together, the P sigma was P1 sigma and P2 sigma. So this is a logical, it's not a syntactic AND, it's a logical AND operator. And that is same as P1 sigma prime and P2 sigma prime because of what we just argued, and by the semantics of and, this is the same as the sigma prime, which is P under sigma prime. So far it's I mean, just in some sense straightforward applications of structural induction. And the last case is requires a bit more care. So here we have to see, let's pick any integer n, and then think about extending the sigma or changing sigma by binding x to n, also changing sigma prime with binding x to n. If you do so, they satisfy the assumption for P1, which is the body of this universal quantification. Why is that? For P1, the free variables are either already free variables in P or this bound variable x. So that this assumption say every free variable sigma and sigma prime should say the same. In this case, for P1, that means for every free variables of P, they say the same thing. For variable x, they say the same thing. So it satisfies this assumption. So therefore, what we know is that for any P1, for any natural number n, integer n that we pick, P1 and the sigma xn have the same value of P1 sigma prime under xn by induction hypothesis. So what we have shown that for any n, if we extend sigma with this x, or change sigma with this binding, x gets mapped to n, sigma prime with the same binding, the body of the universal quantification will have the same meaning. So now we go back to the original one, P, the sigma, that is equivalent to say for, it's true when for natural number, no, for integer, P the sigma x to P1 and the sigma x to n has to be true. But as we showed, this is say the same thing as P1 and the sigma prime x n is true. And let's say the same thing as P and the sigma prime is true. So the proof is not very difficult, but I go through the proof because so that you know how to complete the proof with this type of this structural induction proof. Okay, so but this is an important property, and intuitively what it tells us is the meaning of the assertions only depending on the free variable. That's what we expect, and our expectation is met. But the second important property is the substitution. So maybe just go up. So this is correspondence. And so second property is substitution. It intuitively tells us correspondence between semantic and syntactic substitution. So this is what we learn. And then what I call semantic substitution is a bit informal word that I'm going to explain in the theorem. So the theorem says the following. If we have two states, so we are given assertion P, and then we are given two states, sigma and sigma prime. And also we are given substitution delta. But then this is sigma and sigma prime satisfy some condition. The conditions say for all the sigma prime of x has the meaning of the delta of x on the sigma for free variables of p. So if you ignore this part of for the moment, what does this really tell us is that sigma prime, intuitively, this means that sigma prime is obtained by, sigma prime is obtained by applying substitution on sigma. So sigma is a mapping, and sigma is, in some sense, this is what this tells us. Sigma prime is something that we obtain by applying the substitution on the sigma. I mean, this is an informal word. And the formal definition property that I just told you is a sigma prime of x. It's the same as delta of x on the sigma. So if that's the case, then we have the following property, which is if we have a p and apply the substitution and then interpret it on the sigma, that is the same as apply p, to take the semantics of the assertion p on the sigma prime. And again, if I use an informal description, and the informal description looks like this: p sigma is the same as p, where we, instead of applying substitutions on the assertions, we apply substitution on state. So this is an informal, but it will give you some idea. You say that there is a correspondence between applying syntactic substitution and then semantic substitution. So this theorem substitution lemma is really telling us, if you happen to do some reasoning about outcome of assertions after applying the substitution, you may as well do, I mean, you get almost all the results that you care about by applying the substitution on the state directly. So it will allow you to avoid the case analysis and have a better understanding about what's going on. So I'm not going to prove this, but that's the important fact. So it's emphasized again, it talk about correspondence between syntactic and semantic substitution. Now there are two important consequences of this. The first consequence is, so now let me record some notations. So we write substitutions as x1, e1, x2, e2. So substitution can be written as like this, xn, and that means you replace x by e1, x2 by e2, and so on simultaneously. Okay, not one after the other. You apply this substitution, replace x1 by e1, x2 by e2, and so on. For all the other variable, it doesn't do anything. So that's the definition of substitution. Okay, and also other notation is something that we already used. I mean, sigma, the x has a value n. It means it's a state where variable x now gets mapped to n. For all the others, it maps to the same as y. So if you apply y, say that it's n if x and y are the same variable. Otherwise, it's sigma of n, sigma of y. So in a sense, this is saying state update operation. So using this notation, we can talk about the corollary. What this corollary tells us is, if for every formula p, if you apply this substitution, x1 gets mapped to e1, xn gets mapped to en. Apply this substitution and evaluate the compute the value of assertions on the sigma. Let's say the same thing as taking the p where you apply the substitution on state as an update operation. X1 becomes E1, X2 becomes E2, and so on. Xn becomes En. So here's some assumptions. The assumption is X1, Xn are distinct, so they are not the same. Okay, so this also make it a bit more clear that syntactic substitution, the substitution correspond to semantic substitution. Well, you can, another way to think about semantic substitution is state update. So substitution corresponds to the state update. And although I'm not going to tell you now, I mean, this is closely related to the, so if it's X1 and Xn are not distinct, then it's a bit, I mean, it's not a well-formed definition, because the reason we are using this X1 arrow E1, Xn arrow En is a way to specify a map from variable to expressions. So they are not distinct, so that means the map is defined ambiguously. So it's a ill-formed application of this, I mean, or ill-formed the phrase. Okay. So the one minor comments that I mean, Juan, if you couldn't understand, you can also ask me again. Okay. So so that this correspondence will later play a very important role. If some of you who worked on program verifications, you may have heard about so-called weak precondition. So weakest precondition. And then this weakest preconditions, I mean, this equality actually plays is essentially the weakest, it's just something that justifies the weakest precondition for assignment. So if you don't know what I'm talking about, that's okay. I'm just saying this is some useful results, but at the same time, it's useful for application as well, so where the application is program verification or automatic program verification. I mean, if you are working on program analysis, is related to so-called backward program analysis. Okay, now the last bit is about renaming. So the renaming lemma said, if you have a universally quantified formula, the sigma, and that have the same meaning of for y, p, so let's see. That's right. I'm sorry. I think Seungmin is right. I have to put sigma here. Is it correct? Thank you very much. So I have to put sigma over there. Okay, for the corollary, it said that this is the case, which means renaming doesn't really change the meaning as long as renaming is done correctly. So variable y is chosen as something which is not a free variable of p except free variable p except x. Okay, so this means that renaming preserves the meaning, and I mean, it's not exactly the application of the lemma, but I want to give you, I will give you 1 minute to prove these things from the substitution lemma. So, and your argument is informal, that's completely okay, but I kind of want to see how all things are going to get together. So exercise is to prove this. Yeah, I'll give you 2 minutes to do so. So, okay, so the proof is, I mean, strictly speaking, it doesn't really directly follow from the corollaries, but so, I mean, the actual proof, if you look at the proof of the corollary and substitution lemma, you can see why this renaming, the soundness of this renaming, or meaning preservation of renaming is going to be true. And I'll just give you a semi-formal argument about how to see this. Okay, so if you, in this case, let's consider the substitution delta, which is, it doesn't do anything. I will write it as a empty to means that identity substitution. So that's, if you look at this corollary, that means we have an x1 get mapped to e1 and so on. Essentially, this list is empty. So that's the substitution we are talking about here. Then by the corollary above, what we do know is that if you have a 4xp, apply this substitution, which isn't, let's just write it as an empty. Empty substitution, and then evaluate on the sigma. That is the same as meaning of universally quantified formula, where we take sigma and then do some update, but there is nothing to update. So I mean, this is with dodgy notation, but this is really means the sigma. Okay? Nothing to be updated because this substitution is identity and doesn't do anything. So that's the same as meaning of original universal quantification. Now, if you look at the definition of this substitution, the definition of substitution of this guy is defined like this. So it's a syntactic operation. We replace x by x new, where p get replaced by this empty substitution where, and we update x by x new. Okay, and then what is x new should satisfy, x new should satisfy, should not be a free variable that appearing in empty substitution applied to y, and for all y, which is the free variables of p except x. Now, if you simplify whole things, this condition below, say the same thing as, because empty substitution just means identity, it means that x new is not in free variable of p minus x. Then applying these substitutions, the one written here, this is say the same thing as p where x gets replaced by x new. Okay. And then although for when it is defined the substitution, we talk about particular choice of x new. Actually, the proof of the substitution lemma, I mean, doesn't really depending on our specific choice. Any different choice will still make all the things to be true. So by going all these things, we can say that, I mean, if we have this substitution on the left-hand side here, and let's say is the same thing as, have the same meaning as for x, px new, sigma delta. So that's how we can prove these two things are equal. Okay. So I mean, of course, I mean, this step requires a bit more careful, I mean, the understanding, but the point I want to make is that if you do all the proof of the lemma that I showed you, I mean, actually the proof can be modified slightly to derive this correctness of renaming. Okay, so what does this mean? This means that this binding operator is a preserved, I mean, renaming of the binding operator preserve the meaning. In other words, this binding operator, the specific name x introduced by this binding operator doesn't really matter. Okay, that's what we are expecting, and that this theoretical analysis confirms our expectation is hold for this language. Okay, so that's it for the whole part of this predicate logic. So we talked about abstract syntax and syntax directive definition, denotational semantics, inference rules, binding, and a few properties about the binding and the semantics. Do you have any questions about this? Okay, so if you don't have any questions, I will move on to the next topic. So now we are really studying, we move on to chapter 2 of the textbook, which is about the imperative language. So now we are really studying a proper programming language. So this is called chapter 2, simple imperative language. So most of the programming languages have, when there are a few ingredients which exist, and most of those programming languages combine these high-level ingredients to, in one way or another. And this imperative computation is one of the ingredients. So maybe overview / motivation. And there are many ingredients in programming languages. Or you can say higher level design principles. Programming languages. And then what are those higher design principles? One is imperative computation. So support for the imperative computation. And another one is called applicative computation. So it's a language designed for supporting applicative computation. And there are object-oriented principles, and so on. There are multiple of these things. And then but these imperative and applicative features are, in a sense, two key most important bits in high-level language design. So what does imperative computation mean? Imperative computation means that we are presuming there is something called states. We already talked about states, but states are essentially computer memory, which can be divided by variables. And then the perspective of imperative computation say that computation happens by reading some values from this state, by reading the values of variables and changing it and storing in a variable and so on. So this perspective tells us computation proceeds by read and writes of variables. So that's a perspective of imperative computation, and most of the programming languages are designed to support this type of computation. Applicative computation is a bit different. The perspective there is that the key step of computation is function application. So as a main mechanism, for computations. So in a sense, most of the programming languages already have a support for applicative computations, because in almost all the programming languages, you can define procedures, you can apply the procedures and so on. But there are programming languages, especially something called functional languages, where this support for applicative computation is very strong. For instance, OCaml, Scala in some sense, and also the closures, and nowadays even Java. There are many languages which provide the proper support for applicative computations. Object orientation and so on, they all have a different perspective about computation. So object-oriented principles, in some sense, is that instead of variable, we are stored, the, in a sense, granularity of states is lifted from simple variable to the more sophisticated things. So according to what I heard, either John Reynolds or Beckers, somebody told me, said they complained about imperative computation by saying imperative computation is like doing computation with pigeonhole, because you take the pigeon from pigeonhole and you rotate, you just sometimes put this pigeon into a different pigeonhole and so on. So that's what, I think either Beckers or some famous computer scientists complained about. They make fun of the idea of imperative computation. And the story I heard was that John Reynolds said, oh, actually, but for object-oriented languages, more interesting thing happens. So he viewed the O as a turkey hole. So in the turkey hole, the hole is much larger. And instead of pigeons, you can do more operations, like you can rotate turkey into the hole and so on. So principles are similar, but the basic unit that we are dealing with is much larger. But anyhow, there are these key principles, and one thing that we are studying in this chapter is this imperative computation. Language for studying this imperative computation. So one objective that I want to get from this course, one big lesson or some skills that I want to achieve by taking this course is that I want to be able to reason or analyze a new programming language, okay? So I have a machine learning colleague, and he told me he wants to work on program synthesis, but what he told me a long time ago is that for him, thinking about language itself as an object of study instead of programs as an object of study is very foreign, very unusual to him. But one of the things that people learn in programming language training is to view each programming language as an object of study and analyze it. So for instance, if you want to analyze some aspects of imperative computations, and typically if some researcher want to study about some aspect of imperative computation, they typically look at the language that I'm going to present this lecture and the next lecture and so on. So in the imperative computation, I guess all of you know about this. So there are simple things that you can do. Maybe I can write it. Or if you compute the sum of all the values from 0 to n, then you can write this program like this. Initialize x to 0, and you say if x is less than n, do something. The body of the loop, we said we store y. Y is also initialized to 0. So we said that y becomes y plus x, and then we increase x by 1. Okay, if you write program like this, often you do better indentation, but if you write program like this, this is a program that will add all the numbers 0 up to n minus 1. And then if variable y will store this. So that's a kind of example. Then you can think of all sorts of examples which does the computation by this state updates. And then by studying this, while we are studying this language, we will look at a few important bits. And one important bit that we're going to study is that we will look at how to handle So let me just put a keyword first. We'll look at something called domain theory. that allows us to handle, allows us to interpret the while program correctly. Okay. Why that's the issue here? So unlike predicate logic, in this type of a language that I'm talking about, some strange behavior can happen. The specific strange behavior is non-terminations. If you write program like while true to skip, this program will go on forever. Okay, so there are some strange behavior, and to also the notion of while is a bit like recursive definition, and so providing the appropriate meaning of while requires a lot of care. So we're gonna study something called domain theory that will allow us to give a denotational semantics of this language. In the presence of while. And then the other bit that we're gonna study here is we look at something called some language design principles, especially we look at something called Syntactic Sugar. So there are some ways of extending a programming language. Some of extension of the programming language brings dramatic change. So the intrinsic nature of your language changes dramatically. Some other changes or additions into the language do not make such a dramatic change. It makes programming easier, but from the perspective of properties of programming language, things do not change that much. So syntactic sugar is the second kind of change in a programming language. It makes things, allows us to extend the language very easily. It's like a macro, but it doesn't really change fundamental nature of the programming language. So that's a syntactic sugar. The last bit we will look at is, when we define the denotational semantics, we didn't really ask the following question, which is how good the denotational semantics is. So ask the quality of denotational semantics. So in a simple programming language, like predicate logic, this issue of quality doesn't really appear that often because there are not many options available. But more sophisticated language, this type of question appears. And we will study two concepts here. One is called soundness. The other is called full abstraction. Something that we will not consider here, and I think it doesn't appear in this textbook, but appears in other peer book, is something called adequacy. ACY. And then this is another important properties about the denotational semantics of a programming language. Okay, so this is an overview. We're going to study imperative programming language, and in doing so, we will learn. Not just studying the imperative programming language, we learn very generic tools that we can use to analyze any programming languages. The first is domain theory. Second is the idea of syntactic sugar, and also a brief discussion about the quality of denotation, how to measure or how to analyze the quality of denotational semantics. Okay, so let's start with the syntax. So the definition of the syntax will be just like what we did before. It will be an abstract syntax specified by abstract grammar. This means that we're gonna use the grammar notation mainly to specify all the finite derivation trees, or the finite parse trees. And so we are not going to think about any issues for parsing, like ambiguity and so on. And more mathematically, and also this abstract syntax means that all the syntactic elements that we are talking about are going to be a finite trees according to this grammar. But more mathematically, this abstract syntax can be understood as an initial algebra. Abstract grammar can be understood as specification of appropriate signature for that algebra. Okay, so what's the syntax in this case? We have three types of non-terminal. One is called integer expression, which is the same as the integer expression that we looked at before. So I'm not going to write it down. There are constants, variables. Yeah, just point out there are variables. And there are unary and binary operations and so on. And for Boolean expression, it's essentially identical to the assertions that we studied in predicate logic. So I will just, except that we don't have a universal and existential quantification. So I'm gonna show you only one case or two cases. You can have an equality between two integer expressions. Also, we can have in Boolean expressions, negation of Boolean expression. Okay, so these are, in a sense, a bit cosmetic aspects of it's the kind of subsidiary aspects of this imperative programming language. The important bit is what I'm gonna explain to you now. So we have a third non-terminal, which is called command. And we have multiple different commands. The first command is a skip, which doesn't do anything. The second command is an assignment, which have a variable on the left-hand side, and then integer expression on the other side. And then so we have an assignment. And then the third one is called sequential composition. Fourth is if then else statement. Then commands. And then the last bit is a while statement. So in fact, just like I told you before, most people who are doing research on programming languages, if they want to present their key ideas for static analysis or maybe new programming logic or any type of their work for imperative features, the imperative aspect of a programming language. This is the kind of programming language that they use. And also I myself use quite a lot. Key things are should have a basic command, which are typically skip and then assignment. And then we have three compound commands, sequential composition, if then else, and then while statements. Okay. Now I said the imperative languages are like the ones where computation proceeds by looking at the values of accessing variables and updating variables. And the assignment here is the main mechanism to update the variables. And then when the reading of the variable happens by integer expressions in the assignment and then these two Boolean expressions. Because expressions may contain variables, so variable access happens there, variable updates happens by the assignment. And just like I said, this is abstract grammar, and abstract syntax means all the finite derivation trees in this abstract grammar. And just you can also view this as an initial algebra for signature generated by this abstract grammar. So what does this tell us practically? That tells us we now, for this language, we can do syntax directed definition. Also, we can do structural induction. They are all available. Because we are using initial algebra on finite derivation trees. So, okay. So that's the syntax of this language. And now remaining maybe 5 minutes, I'm gonna tell you about how to specify the semantics of language and what kind of issues that will arise. Now, the next question we want to say is, okay, this is a syntax. You have a pretty good understanding about how the program behaves. Now that the question becomes, can we specify the semantics of this language well? So it's a denotational semantics. So what is a potential issue? Okay, so the issue is now I said the denotational semantics in this language will become a mapping from the abstract phrases, which are commands, to something. Okay, so let's put something at some set S. Okay, we don't know what it is, but we say some set S. Then, maybe just like what we did before, maybe we can use a syntax directed definition to give a meaning. But this doesn't really work. Here's a reason. Okay, it doesn't really work in the sense that if you want to do something sensible, something that looks okay, you will encounter some problem. So here's something that we expect to be true. Suppose we have a while Boolean expression to command C. Okay. So then we expect that this one is same as unrolling the loop once. So which means the same thing as unrolling the loop once, which means that if P is true, then we run C once, and then run the while loop. Otherwise, it doesn't do anything. Skip. Okay, so that's the intuitive equality. Now, in this, but because this is an intuitive equality, we are expecting if we define the denotational semantics in the right way, then the left-hand side and the right-hand side should have the same meaning. So now this one becomes a real equality. So you can say this may be the requirement of denotational semantics. And I said denotational semantics is defined inductively in terms of the subphrases. So if you write down the definition of this if statements, sequential composition, and so on, there will be some mathematical expression, but at some point, we will have the inductive core for something like this. So there's a mathematical expression, but at some point, semantics of while B to C will appear because that's a subphrase. It may appear twice. C and so on. So now what does this mean? This means that now if you write it down in this part, which is the surrounding part of this while, as a function f, then really this means that this meaning of while should be the same as applying function f to the meaning of while again. Okay, so that's what we are expecting by first assuming this equality to be true, and then the generic form of denotational semantics. So what does this mean? This means that this while this thing is a fixed point. Of the function f. Okay. But we know that if you have an arbitrary function, the function may not have a fixed point. For instance, if you define function g, which take natural number to natural number, so g of x same as x plus 1, this function will not have a fixed point. But it looks like if you want to give a semantics of a while, somehow things are all arranged in the right way so that the capital F that's kind of induced from this definition will have a fixed point. So what we're gonna do in the next on Wednesday is to define the so-called domain theory. Domain theory, in a sense, identify some invariant properties that exist in this while language and formulate it mathematically, so that it will allow us to prove whatever that comes in these definitions, like this function f, is guaranteed to have a fixed point. So we can define, and then in fact we will define the meaning of while as least fixed point. Okay, sorry for overrunning for 1 minute, but I mean that's it for today, and I hope to see you on Wednesday. So I'll be here about 5 minutes. If you have any question, you can ask me.